And so again, Brenda Egan, STEM Career Counselor. I'm here along with Marina Bograd, who is our professor and chair of engineering department. So Marina's here in the classroom and I'm here online. So welcome everyone. Thank you so much for being here, especially to our speakers. This is the last but not least event of our NK speaker series. And today we have Dr. Catherine Stoll and Dr. Drew Wenninger of MIT, and they're going to be discussing PIC sensors, optoelectronic semiconductor packaging and testing, in addition to their respective theses. So I just wanted, before we get started, just a few housekeeping items. There may be an interruption due to the testing of our emergency notification system today between 1 and 2. So if it disturbs us, it would only be for a second, but just so you know, that's what it is. And at the conclusion of the presentations, we're going to have time for Q&A. So Marina Bograd will be fielding the calls from the classroom, and I'll be monitoring the online chat, so feel free to enter your questions as you think of them. We always love student feedback, so we have a link in the chat right now, and Professor Bograd will show us a QR code at the end. If at any point, just go ahead and get the survey done towards the end of the program, and or copy the QR code and go do the survey that way. So thank you so much, and we're about to get started. I don't know if someone wants to go first, Dr. Stoll or...
Sure, I'm happy to go first.
Okay, great. Thank you so much.
Of course.
Are you looking to share something?
Yes. Can you guys see
you got it.
that now? Okay. All right. Can you still see in present mode now?
Yes, we can still see it. It's not in slideshow, but we can see the individual slides.
Okay. I'm going to try it one more way to get it in slide mode for all of you.
If you have multiple screens, sometimes you just need to share a different screen. I don't know if that's what's happening.
Yeah, I think so. I'm just going to share the whole. Oops, now it's frozen. So sorry. Now mine's kind of frozen.
If it's easier and you want to send me your file, I can share on my end if that works better.
Yeah, I might unjoin and rejoin really quickly and see if that fixes it, if that's okay.
Sure, sounds good.
Okay, 1 second, sorry.
No worries. And Drew was back.
Yeah, I was going to say we should start with Drew, but at this point, let's let Katie come back in, I guess.
Yep. We'll see if that doesn't work. We'll get Drew to go first. Maybe.
Should I go first? Sorry, I had to quit and rejoin to let it record me.
No worries. So Katie was having a little trouble. She's coming back, a little trouble sharing. So if she still has trouble sharing, she'll be sending me files, and then you will go first.
Okay, sounds good.
Hey, what building are you guys in?
Are you talking to the MIT?
I'm talking to, where is this meeting so we don't have to be on virtual?
Oh, so we are at Mass Bay. Are you a Mass Bay student?
Forget it. Forget it.
Okay, so now everyone can see my screen, hopefully,
We see you actually.
and in presenting mode now.
Yeah, but like we're seeing you on camera and the slides behind you, which is very cool.
All right.
I need to learn how to do that.
I'll stop share. Can't say that that was the goal.
Okay, the best
oh, there we go.
inventions were
Okay.
found by. There we go. Awesome.
All right.
Yay.
Sorry about that.
Sorry.
All right. So now I'll get started. Thank you again for the introduction. My name is Catherine Stoll, and I just recently defended my PhD thesis at MIT, and my research has been focused on photonic integrated circuits for chemical sensing devices. So today in this talk, I'm going to be starting with kind of a motivation for mid-infrared photonic integrated circuit chemical sensors. And then I'll talk about one specific device that I designed and the motivation for the materials that we selected for our waveguide components and photodetector components. And then finally demonstrate some chemical sensing with this fully fabricated device. So right now, there's a growing global market for sensors for a wide variety of applications, ranging from industrial process control to chemical and gas detection and patient health assessment. There are many advantages for integrated photonic sensors for these applications. Specifically, they offer very small size and very low cost to fabricate. And they also have very low power requirements and simple electronic integration that require very low maintenance over time. So these are stable devices that can be put in a lot of different environments and used for all of previously mentioned applications. On the left, you can see kind of a schematic of a simple photonic integrated circuit where you have a light source coupled onto this photonic chip, which has the gray background here. And this blue component here is showing a waveguide, which essentially guides light through our device, and then a readout electronic component that does basically all of the data analysis for this device. In addition to these small size, low power, and cost advantages of photonic integrated circuits, they also offer very high sensitivity and specificity so that we can analyze different chemicals of interest. So what are the different methods for photonic chemical sensing? Photonic chemical sensing revolves around changes in the complex refractive index, which is given here as a real and imaginary component. So one common method of photonic chemical sensing is refractometry, which senses a change in the real refractive index of the surrounding environment, or this real part of the refractive index. However, this method has very poor specificity because many chemicals can induce the same change in the refractive index of the light. On the other hand, if you take a look at the imaginary component of the refractive index, there's another method called optical absorption spectroscopy, which measures the absorption of light from interaction with the analyte. This type of spectroscopy is governed by the Beer-Lambert law, which is given here, where the transmission of the optical signal is an exponentially decaying function of the absorption coefficient of the chemical of interest, the analyte concentration, the evanescent field, which is essentially how much of the light is interacting with the given chemical, and the interaction length, which again is how long the light signal is interacting with the chemical that we're trying to detect. In contrast to refractometry, this method offers very high specificity because, as you can see in this plot here, the absorption coefficient, which determines how much of the signal is absorbed by our chemical of interest, is very unique for different chemicals. So you can see for water here, given by the blue, it has a strong absorption coefficient around 6 micron wavelength and around 3 micron wavelength. But methane gas has a strong absorption coefficient given by the red here around 3.5 and 8 microns. So by testing at different wavelengths, we're able to determine exactly which chemical we're detecting based on these unique absorption coefficient spectra. So my work has been working with optical absorption spectroscopy to benefit from this high sensitivity and specificity of different chemicals. So here we're looking at the photonic integrated circuit design for one of my devices, where again, we have that light source coming in from the left, coupled into our photonic integrated circuit, which I'll describe in a little bit more detail later, and then coupled into our readout electronics. So one of the first components that we need to consider when designing a photonic integrated circuit is our waveguide material, which again is what we use to route the light into different components on our photonic integrated circuit, and is given by this dark blue line on our circuit. So one of the most important components for this waveguiding material is that we want it to have a very high refractive index, given by the y-axis over here, for our target wavelength. Essentially, if we have a high refractive index, this helps to pull the light into our waveguide so that we can efficiently route the optical signal on our chip into different directions. Additionally, we want to have a very low extinction coefficient given by the y-axis on the right here, as the extinction coefficient determines how much of the signal is absorbed by our actual waveguiding material. And since we only want the light to be absorbed by our chemical of interest, we want the extinction coefficient of our waveguide material to be very low. So right here for our target chemical, in this case, around 2 to 3 microns, we have a very high refractive index given by the blue line here, and a basically 0 extinction coefficient given by the green line here, for a material called germanium antimony sulfide, which is a chalcogenide glass, which enables us to achieve a single mode waveguide, which you can see here in the right, is a simulation at our target wavelength of 3.3 microns, where we have all of the light very well confined in this outlined square here, which is a cross section of our waveguide. So this will enable us to route the optical signal on our chip very efficiently with low optical losses. So another component to consider when designing a photonic integrated circuit for chemical sensing is the evanescent field of our waveguide. So as I mentioned before, for optical absorption spectroscopy, transmission is a function of the absorption coefficient, the concentration of our chemical, and most importantly, the evanescent field and the interaction length. So the evanescent field is how much of the light is sitting outside of our waveguide. So you can see on the edges here that there is a little bit of light that is outside of our actual waveguide, and this light is interacting with the surrounding air or whatever chemical we're trying to detect. In this plot on the right, since this is an exponentially decaying function, that you can see that for a larger evanescent field, say for 25%, given by this brown line here, that for the same concentration of this chemical, having a larger evanescent field for the same concentration induces a much larger change in the transmission, say about 70% of the initial signal for a 25% evanescent field, whereas if the evanescent field is only 1%, we would see approximately all of the signal transmitted for the same analyte concentration. So in order to increase this evanescent field, we can make our waveguide narrower or thinner, and this will help to expose more of the light outside of our waveguide and improve the sensitivity of our device. Finally, since this exponentially decaying function is also a function of the interaction length of the optical signal with our chemical of interest, we also want to increase the interaction length of our waveguide. However, since optical chips, one of their benefits is that they're very small, we want to maintain a large interaction length over a small device footprint. So we typically use a spiral waveguide that looks something like this, that has a very small area, but but a very long interaction length to improve the sensitivity of our device. So now that we've designed what this optical circuit looks like, in order to fabricate these glass waveguides, we use a photolithography process. Essentially, we have a silicon chip that has a silicon substrate and an oxide, a bottom oxide to insulate from our high index substrate material. And we coat this with a double layer photoresist, which is essentially a little polymer that we use to pattern our waveguide devices. We then pattern this device using an electron beam exposure and develop these 2 layers of photoresist to get a nice undercut. You can see that the layer on the bottom is slightly wider than the one on top, and this helps us to pattern our waveguides very effectively in the end. And you can see an SEM image here of the actual fabricated device with a cross section that matches our desired geometry. So after patterning these polymer layers with the desired dimensions, we then deposit our glass waveguide material through a physical vapor deposition technique. Essentially, this is just applying heat to our powdered glass material in the bottom of our deposition system, and then it causes evaporation of the material in a gaseous phase that deposits a very high quality material onto our chips at the top of the chamber, since this is done at a very low pressure. We then put this material in a solvent, and it causes dissolution of the excess polymer materials on the sides here, and just leaves behind our desired waveguide with the patterned dimensions from our E-beam exposure. So here you can see an SEM image of a cross section of one of our fabricated waveguides with the desired dimensions of around 2 microns wide and 1.2 microns thick. You can see that the sidewalls are a little bit curved compared to the square geometry of our initial simulation, and this is just due to the undercut process from that patterning of the polymers. So having developed our waveguiding material, the next most important component on these devices is an integrated photodetector that will allow us to extract this optical signal from our devices. So I guess to start, what is a photoconductor? So a photoconductor material is a semiconductor material that has a small band gap between the valence band given here and the conduction band given here. Typically, there is some distribution of electrons sitting between the valence band and the conduction band at steady state. And these bands are typically flat with no applied bias. When you apply a bias across these 2 materials, it causes a bend in the bands, and it will cause the electrons to drift in either direction based on the flow of the electric field. When infrared light is exposed, as shown upon this semiconductor material, it causes excitation of the electrons from the valence band to the conduction band, which then causes a change in the voltage that we're measuring across the semiconductor material. So by measuring the change in the voltage across this material, we can then estimate how much infrared light is actually being illuminated on these photoconductor films. So the most important properties of this photoconductor material is the band gap, which determines what wavelengths of light this material can absorb. So in this case, you can see the extinction coefficient, which is essentially the absorption given by this plot on the right and indicated by the dashed red line here. So for this target wavelength range, this lead telluride material has a very small band gap and thus a high extinction coefficient at our target wavelength. Additionally, it has a very high refractive index, which again will help to pull the light into this material so that it can be effectively absorbed and generate those electron hole pairs that we need to detect a change in the voltage of our photoconductor. So this is showing here a cross-sectional image of our lead telluride detector with our GSS waveguides. So the lead telluride detector is a very thin layer of just 100 nanometers that sits underneath our waveguide. On the left, you can see a cross-sectional view, and then on the right here, you can see a top-down view of the actual fabricated device, where we have the waveguide of that chalcogenide glass coming in from the left, crossing over a square lead telluride photodetector, and then there are two metal contacts made of tin that are deposited on top of the lead telluride detector so that we can apply that voltage bias and measure the change as we generate those electron hole pairs when the optical signal hits our photodetector. This is showing a simulation of an optical signal propagating in from our waveguide on the left. And as soon as it hits this detector material of our lead telluride, it essentially dissipates very quickly due to the absorption from the high extinction coefficient of our lead telluride material. So having successfully demonstrated the fabrication and design of our waveguiding material and detector materials on this chip, we're now going to look at the system design and why we have a reference and sensing detector that you can see on this photonic chip. Typically, when we're using photonic integrated circuits, there are some unwanted external phenomena that can occur due to laser power fluctuations or light coupling instabilities from our laser source to our photonic circuit. What this can look like is that the input signal can change over time just due to changes with the laser or anything else in the surrounding environment. So in this plot on the left, you can see a schematic of the intensity versus time, where you can see a steady decrease in the intensity just due to some environmental factors that could occur. However, this could be misinterpreted as absorption or intensity loss due to exposure to our chemical analyte. That would also cause some absorption. So in order to overcome this external phenomena, we use a ratiometric measurement technique where we have the initial optical signal split between a reference detector and then a sensing detector. And only our sensing spiral with the long interaction length is actually exposed to our chemical of interest. So as you can see here, both the reference detector signal and the sensing detector signal recover and show this steady decrease in intensity over time, but only the sensing detector signal picks up on the additional loss from exposure to our chemical analyte between this time period. So by taking the difference between these two signals, we can get a much higher sensitivity of our device and realize the actual absorption of our chemical during a given time period. I'll go through this quickly, but in order to extract the electronic signal of our photonic chips, we collaborated with some partners at Politecnico di Milano, which is a university in Italy, and they created an electronic readout system where our photonic chip, which we saw here, is wire bonded to a PCB, and then we plug it into their electronic readout system, and we're able to extract that voltage signal over time for our photodetectors. In order to measure these devices, I just wanted to show a quick schematic of our actual experimental setup in the lab, where over here we have our laser, which shines our signal around 3.3 micron wavelength, which is our target wavelength for this device. It is then routed to our sample stage, which you can see a close-up here, where we have the light focused in this aspheric lens here and coupled onto our photonic chip that is wire bonded to the PCB and then plugged into the electronic readout system. So you can see here some of our initial results of this photonics detection system, where we have the two signals of the detector current versus time. In the green, you have the signal from our spiral detector or the sensing detector here, And in the blue, we have the signal from our reference detector up top that is not exposed to our chemical of interest. So in this test, we caused some external power fluctuations just by decreasing the coupling efficiency of our laser onto our chip. And you'll see that this caused a large dip in the signal around 10 seconds. But when we look at the ratiometric signal by dividing our reference and spiral signal and normalizing the two, this is essentially eliminated at this time period. However, when we drop some acetone onto our sensing spiral around 26 seconds, you can see that there's a very large drop in the spiral signal, while the reference signal is approximately constant. And by taking the ratio between these two signals, there is a very dramatic drop in the normalized ratio between the two signals. So through this method, we can clearly detect the presence of acetone or any other chemical due to optical absorption. So in conclusion, we have demonstrated and designed some glass waveguides that have transparency at our target wavelength in the mid-infrared and a high refractive index that allows us to achieve single mode waveguiding. And then with lithographic patterning and liftoff techniques, we were able to pattern these waveguides and demonstrate a low propagation loss at our wavelength. We also integrated some lead telluride detectors that are functional at this wavelength due to their narrow band gap that enables generation of electron hole pairs when the infrared signal reaches this photodetector. And finally, with our ratiometric readout system, we're able to achieve very high sensitivity and acetone detection at our target wavelength of 3.3 microns. And I would also just like to add, in this presentation, I focused on acetone detection at 3.3 microns, but this device design could be applied to detection of many other gases and aerosols with different mid-infrared absorption peaks, such as methane gas or water vapor, and much more. Thank you for listening, and I will open the floor to any questions or pass on to Drew. I don't know what is preferable.
Great. No, thank you so much, Dr. Stoll. That was really, I don't know, just a lot for me. It was so much, I don't even know. But thank you so much. I'm sure the students got a lot more out of it than I did because it's not my area. But yes, we'll actually just want to remind people that we can have questions in the chat. And we probably will take the questions at the end. I think that would be best. We'll have Dr. Weniger go now. And then just as a reminder, there's a link to a survey as well in the chat. So if you get a chance to do that. So take it away.
All right, sounds good. Let's see if I can. What do you all see?
So we see your slideshow, but it's not, I mean, your slides, but it's not in slideshow.
Okay. Better?
Yes.
Okay, cool.
Yep.
Yeah, so thanks for the intro. I'm Drew Weninger. I'm a recently graduated PhD student from MIT, and I have the chance over the next 20 minutes or so to talk to you guys about optoelectronic packaging. So over the course of this talk, hopefully we can answer a few questions about what is semiconductor packaging, why is it important, and then different types of questions about what types of electronic packaging technologies are used, what types of photonic packaging technologies are used, and then briefly go into, just for a second, some recent results from a photonic coupler that we developed at MIT. So that's the goal. Hopefully I can accomplish that. Let's see here. So just in general, what is semiconductor packaging and assembly? It's kind of everything that comes after you make a chip in a foundry. So you make a chip on a wafer, and then after that, even the process of dicing and singulating the wafer, picking and placing the chip that you've diced away onto an interposer or a substrate, which then probably gets connected to a printed circuit board or something else, all of that is lumped into packaging and assembly. So it's just the process of connecting these chips and devices to a system or a network, or the outside world, essentially. And so it's really become important because of the trends that are happening with respect to the performance of transistors on chips. So if we look, like, let's say over the last 50 years at the performance of transistors on electrical chips, it's been following Moore's law in terms of improvement. Roughly it doubles the number of transistors and the performance every 2 years or so. Maybe some people say 18 months. But every 2 years-ish, you're doubling the number of transistors and the performance. But that improvement in performance stopped around 2005, actually, with the stopping of Dennard scaling. And so since that point, we've been continuously increasing the number of transistors, but the performance doesn't necessarily scale at the same rate. So we're not getting as much bang for our buck for every transistor that we add onto the chip. Now, life has gone on since 2005. It's not like things stopped in their tracks. And that's been mainly due to some creative ways of incorporating multiple cores per chip since that point. But today we're running into issues with respect to the physical limit of how many transistors can be packed onto a single die and how challenging that is. I mean, even with the advent of really, really advanced tools like the ASML extreme UV lithography tool, it's extremely difficult to continue doubling transistors every 2 years. And so in response to that, there's been increasing interest in looking at packaging, which has been traditionally kind of uninteresting most of the time, in order to figure out ways that we can incorporate multiple chips, either through stacking them or putting them side by side, in order to increase the performance of the system as a whole. Because at the end of the day, that's what you care about. And so this is the reason why large semiconductor manufacturers such as TSMC or Intel, Samsung have been looking at different types of advanced packaging methods of 2.5 and 3D stacking of chips. And while one of the main applications, that's driving this, people usually point to things like artificial intelligence and data centers, and those are very important. But this is the importance of advanced packaging and the importance of advanced chipsets, and the ability to process significant amount of data is important for tons of different applications. And one of these that's on the cooler side can be highlighted by some recent data from even last week. So last week there was some results that came out that showed the mapping of the neuron network in a mouse brain. And previously it had been considered impossible that you could take a millimeter cubic volume of any brain and map what the neurons were doing in that millimeter by millimeter by millimeter. But they did it by taking cross sections, imaging cross sections of the mouse brain and basically stitching them together to form the circuitry. But the interesting thing is that it took about 6 months to complete this imaging process, and it produced about 2 petabyte of raw data. So 2 petabit is 2,000 terabyte, which is about 22 years of high definition video. So this is an example, even within biomedical applications, of the need for very high performance chips and high performance packaging in order to process all of this data, even outside of like the artificial intelligence space and all of that. So with that, I'd like to go into like different types of electrical packaging technologies and then move on kind of from there. So when you have an electrical integrated circuit, there's usually 2 ways that you can connect it to the larger system. One of those is through wire bonding, which is kind of exactly what the name suggests. You take a gold or an aluminum wire and you fuse one end onto a metallic pad, which is on the chip itself, and then fuse the other end onto a pad that's either on another chip, or it could be an interposer or a package substrate, and then you move on to the next bond. And this is a serial processing method where one bond is made after the next, and you can do that manually if you are just in a research and development environment, or you can do it in an automated way where you can actually make each bond. If you use a ball bonder, you can make about 20 bonds a second. And so this is by far the most ubiquitous bonding method and method for connecting electrical die, or even making electrical connections to photonic integrated circuits, is through wire bonding. Even if you look in the literature, over or from 2006 to 2021, there's about 3,500 papers on wire bonding, and there's only 140 of them on kind of everything else. And so while the rest of the talk is kind of focused on the advanced packaging technologies, that is to say that wire bonding is still like the dominant method today. But those advanced technologies usually come into effect with solder bumping. So solder bumping is the idea that you have, maybe on your chip, you just have a metallic pad, maybe it's gold coated, and then on the lower either printed circuit board or interposer, you have a solder joint, which could be something like tin silver copper. Even in the past, it was lead tin, but getting away from lead for obvious reasons has been a trend in recent years. And so sometimes gold tin is used, but usually it's something that has a melting temperature below 280 C, so that you can melt the joint and form a connection between two chips without affecting all of the transistors that are within the chip itself, which have certain doping distributions that are affected significantly if you go above a few hundred, 300 or 400 Celsius, right? So and the idea in solder bumping too is not only that you are going to fuse these joints, but you're going to do it in a flip chip bond, where you take the top chip and you flip it over essentially and form a chip sandwich between the top chip and then the lower interposer or substrate or whatever you're trying to connect to. And the advantage of doing this, although it's more complicated, is that with a single bonding step, you can form as many electrical connections as you can fit across the surface area of your die. So if these bumps are at a 10 micron pitch, you can fit thousands of them across the surface of your chip. So in terms of flip chip electrical bumps, this table here is kind of showing you the progression over the last few decades towards smaller and smaller bump sizes. So traditionally, these solder bumps were printed using stencils. So you might have a printed circuit board and then a stencil, which is just a piece of plastic with holes over top of it, where you squeegee the solder paste through the stencil and onto the printed circuit board, and then you pick it and place your components on top of the solder, and when you put it in an oven, they can all reflow simultaneously. Now, in order to form smaller joints, the processes that are used are typically electroplating. So instead of just squeegeeing the solder on the surface, you use an electroplating method where you electroplate a small copper stud and then electroplate the solder material in a smaller quantity right on top of the copper stud. And using this, you can get down to joint diameters of around 10 to 30 micron, which is pretty small. Again, just for like reference, the human hair is about 180 microns. So these are in diameter. So these are quite small. Towards the future, folks are looking at direct bonding. So eliminating the solder altogether, as it can contribute to a lot of parasitic electrical losses. And so removing the solder and moving towards copper to copper direct bonding is a direction that the field is headed, because in copper to copper direct bonding, not only do you remove the solder, but you can deposit the copper using an evaporation technique. So when you evaporate, you can form pitches down to 1 micron. And so, you can form an order of magnitude higher number of connections in copper direct bonding. So this is kind of just showing you where we've been and where we're going with respect to flip chip electrical bumps. Let's see here. So those are the types of bumps, but then you actually need to assemble the chips and go through the processes in order to bond. So that's typically done in using, well, it's typically done using pick and place die bonders to start with, no matter what. So in a pick and place die bonder, you insert a wafer that's been singulated, so each chip can be pulled off of the dicing tape, which is usually UV release tape, so you can apply some UV light, and then after that, the die can be easily picked off of that UV release tape. And then that small tip, which is holding the die by vacuum, can place it onto the next interposer or another chip or whatever you want to place it on. So the pick and place die bonder task is just to pick and place die with as high amount of accuracy as it can. This image right here is for the MRSI M3 die bonder, which is the one that we have at MIT that's designed for high volume manufacturing. And so it can hit plus or minus 3 micron with 3 sigma. So it's supposed to hit plus or minus 3 micron resolution 99% of the time, and 1 micron resolution 66% of the time. So after you do the pick and place, you have 3 ways of bonding. One of them is called mass reflow, where you basically do all the pick and place and then insert your system into an oven, and then all of the joints are melted and reflowed simultaneously using convection. This is very good for high throughput because you can, reflow entire printed circuit boards in a single step. Whereas thermocompression bonding, you're actually bonding during the pick and place, where maybe inside the die bonder, there's a heated stage somewhere, and the tip is also heated simultaneously sometimes. And so you apply pressure and force from the top and simultaneously heat in order to fuse the joint in situ in the die bonder, and then you go on and do the next one. This is advantageous because one of the main problems with flip chip electrical bumps is with oxide film buildup. So if a thin oxide builds up on the electrical joint, it can totally prevent a bond from occurring. And so you really want to prevent that. Usually in mass reflow, you apply flux on the surface to prevent that. But another way of doing that is through thermocompression bonding, where the heat and pressure removes the oxide film instead of the flux. And so there's another technique too called laser assisted bonding, which basically locally heats the joint using a laser. It's not that common, but it's useful for heating the joint without heating the substrate or the chip itself. But again, because you have to apply that laser signal to each joint individually, it still has a long way to go in order to ramp up to like a high volume manufacturing setting. So that's kind of wanted to say about electrical interconnects. There's a lot more that I could go into too if there's questions about like through silicon vias or ways for stacking of chips and how the signal gets through those chips. But now I'm going to move on to different types of photonic input output or photonic couplers. And when we talk about connecting or PIC packaging, basically you have to do all the hard work that you do for electrical packaging in terms of like connecting all of your active devices on your PICs using either wire bonds or solder joints, but then you also have to connect the fiber to the chip. And the fiber to chip interface is arguably more difficult than any electrical interface because of the mode size and shape mismatch between the light as it's traveling through the optical fiber and the light as it's traveling through the silicon waveguide on the chip. So in the optical fiber, since it has a core of about 10 micron, the field has a diameter of about 10 micron. And then the silicon waveguide on the chip, if it's 220 nanometer thick silicon, the waveguide might be about a half a micron thick. And so the signal or the mode field diameter is not only much smaller, but it's also highly elliptical because the waveguide is usually rectangular. So because of this big size and shape mismatch, there's very, very inefficient coupling if you just butt couple a fiber to a waveguide on a chip. And there's additional limitations too, besides just trying to match the size and shape of these two modes. So the fiber diameter itself is 125 micron, which might seem small, but when you consider how small the waveguide is, it's actually very large. And the cladding is an issue if you want to make a large number of connections in a small area. So because of the 125 micron diameter, you're limited to 8 fibers per millimeter maximum along the edge of your chip. So if you have a 5 millimeter chip, you can only get 40 fibers in there. And so that's a big limitation, considering that the waveguides themselves can be packed at an order of magnitude closer pitch, right? So there's the fiber pitch. We've already talked about the fact that coupling is difficult because of the big size and shape mismatch. And then there's a low alignment tolerance because of the small optical mode size in the waveguide that typically leads to alignment tolerances of less than 1 micron. And so all of this contribute to a really challenging packaging issue that the field really has yet to come up with an excellent solution for. But I will show you what is typically done. Maybe these are things you're already familiar with, but typically that's either in a foundry, you either use edge coupling or grating coupling. And each one of them has significant pros and cons. So for an edge coupler is very useful if you need low coupling loss and very wide wavelength tolerance. For example, if you're using this in a transceiver, and the transceiver might need to use wavelength division multiplexing, where you're trying to pack in as many wavelengths as you can in a single fiber. This is very useful for that because you can pack in many wavelengths. However, you need a really high quality edge facet here. Usually that's achieved through a deep etching process nowadays, but in the past it was, it was cleaving and polishing the sides of the chips, which is a painstaking process. And so edge couplers are not perfect, even if their performance has gotten a lot better. And the same goes for grating couplers, where you have a significant amount of coupling loss, and they're very intolerant to differences in wavelength. But the advantage is that you don't need a nice clean edge facet. You can stack them in 2D arrays instead of just having a 1D array along the edge of your chip. And then in addition to that, you can the fiber vertically can be placed tens of microns away from the surface. So you don't have to worry about what the cladding is on top of your waveguides as much as you do in terms of the edge coupler. So edge couplers and grating couplers are what are found today in foundry PDKs. If you go to design a photonic integrated circuit, this is what you're going to use. But neither one of them are perfect. So this is, and the fact that they're not perfect is reflected in the cost of PIC packaging and PIC manufacturing. So if you look at the cost of PIC manufacturing, and including packaging and assembly and testing, 20% of the cost is associated with actually making the chip itself, and 80% of the cost is associated with attaching fibers, attaching lasers, final assembly and test. And so that is primarily due to the need to use active alignment of single mode fibers to photonic integrated circuits. So active alignment is basically the process of bringing in an input fiber kind of close to your waveguide along the edge or the top of your chip, and then bringing the output fiber, again, close but not perfectly aligned, and then shining light through the input fiber and doing a scan simultaneously between the input and output fiber in X and Y, trying to line it up to the waveguide. And as soon as that light goes into the waveguide and you see first light, so you detect any type of output power through the output fiber, again, you simultaneously move the input and output fiber to try to optimize the position. So in this plot here, this is the output fiber through the output waveguide, or sorry, this is the output power through the output fiber. And you can see that that output power reaches a peak. And at that point, you know that you're perfectly aligned. And if you were fully packaging the PIC, you would put some UV curable epoxy down along the edge of the PIC and cure that epoxy in place while trying to maintain the position of the fiber, because the epoxy shrinks and expands while you cure it. So because and then you need to do that for every single fiber or fiber array that you bond to a chip. So in a fiber array, maybe you get 8 or 16 fibers for every active alignment step, but it's still a serial process. And so this is why 80% of the cost is associated with packaging and assembly. So in an effort to get around this big cost issue, the There's lots of research going on in packaging in terms of trying to come up with photonic wire bonding solutions that are totally analogous to the electrical wire bond, and then photonic flip chip solutions that are analogous to the electrical flip chip scenario. And both of these, I would say, are in the research and development stage. I mean, photonic wire bonds are starting to catch on a little bit and be used in some industrial settings, but predominantly today, it's still grating coupling and edge coupling directly to fibers. Now, from here, I mean, I'm happy to answer questions like about photonic wire bonds at the end, but I'm going to go into photonic flip chip, and I just have 1 or 2 slides that kind of show one example of a photonic flip chip coupler that our group was researched, although there are actually 3 that I could count that we've studied so far. I'm just going to go into the evanescent coupler results at this point. So the first slide I have is on the design of evanescent couplers, and then the second slide is on the results that we got. So if you want to try to form a flip chip optical connection using evanescent coupling, one starting point that you can use is for coupling between 2 layers within a PIC. And typically that's done using crossed inverse tapers. So if you want to couple between the red waveguide and the blue waveguide, in this case, you might use this single taper layout where your light enters, let's say, through the red waveguide, and you decrease the amount of core material, which increases the size of the evanescent field, like Katie was talking about for her evanescent sensing. You're increasing the size of the evanescent field in this case, and then the opposite's happening in the blue, where you increase the amount of core material. And so at some point, the effective refractive index of the mode between the red and the blue is matched, and light will just jump from one waveguide to the next. And because you're continuing to taper both in the red and the blue, that light never goes back into the red. And so this is kind of reflected by this plot up here. If you plot the effective refractive index of the waveguide, of the mode in the red waveguide, it's shown in red here. And if you do the same for the blue waveguide, it's shown in blue. And at some point, those effective refractive indices, they match, and light will couple from one waveguide to the other. And then it never goes back to the original waveguide. But this single taper layout is actually not so good because, well, it's great if you have your waveguides that can be aligned within a few hundred nanometers, but for pick and place assembly, you typically are working on micron scale alignment. And so in order to get around that, we basically developed a new type of geometry where instead of having one long taper, you put one short taper followed by a long taper. And what that allows you to do is take this point here on the right where the effective refractive indices are closely matched, and you just stretch that point out so that you're interacting, the evanescent fields between the 2 waveguides are interacting over a much longer length. And so in doing this, you can couple over micron scale distances, and you can form a flip chip optical coupler. And so here's some results from a prototype that we made that shows this. So basically what we did is we fabricated 2 chips. We used the pick and place die bonder to place one chip onto the other with a small amount of UV curable epoxy in between. We cured that epoxy and then tested how well we coupled between the 2 chips. And so what you're seeing in the lower left here is an example of the 2 chips bonded together on the testing stage. So you can see the input fiber and the output fiber on the testing stage. And then what you're seeing on the right here is kind of a close-in view of one of the fiber connections. And you can see the signal go in through the bottom chip. It goes through the waveguide on the bottom chip. And then actually right here on the right, this is the waveguide on the top chip. And although nothing special seems to happen at the coupling point, you can tell that light has made it into the top chip by the fact that you see the signal in an infrared camera onto the top chip. And when we measured how much light was being lost through the single taper pair, the coupling efficiency was better than 90%. So this was the first demonstration of such an evanescent flip chip coupler using silicon waveguides. And yeah, it's kind of like a way too quick intro into that, but hopefully that can spark your interest, spark some questions there on that. So just in summary, talked about semiconductor packaging being critical for scaling system performance. Basically, can't do more transistors on a single chip, so we're going to package multiple chips, either stacking them or side by side. Electrical I/O, we talked about wire bonding and flip chip connections, and then using copper to copper bonding for like ultra high density connections. And then for photonics, we talked about the problems associated with fiber to chip connections and how folks are looking towards flip chip optical connections and photonic wire bonding. And I showed you some results from a recent study that we did on flip chip evanescent coupling. So thanks for your attention. Hopefully some questions in there. Thanks.
Super, thanks so much. And I apologize for mispronouncing your name this whole time. So Dr. Wenninger. So
No problem. Don't worry about it.
So we only have a few minutes. Want to remind people there's a survey, and then I haven't had any questions in the chat, but maybe Professor Bograd has some in the classroom.
So I am going to share my screen that will share the QR code if you guys need it. Actually, I don't have to do that. You guys can all see this, right? And everybody else has a link on the chat. I think I saw something in chat. Does anybody have, I know we're really up against time, but does anybody have any questions?
It looks like Alex Reyes has one.
Okay. Anybody? Well, let me. Yep, I have one in the classroom, and then we'll take Alex's.
Okay.
Okay. Wes.
So I don't think I really caught this too well, but I don't really understand when remember her name, but it was like what is analyte in a sense? I don't understand what that really means when you like to say that word.
Yeah,
Could
it's
you-
just another word.
Yeah.
Yeah,
Go ahead.
so the analyte is just another word for saying like the chemical that you're trying to detect. That's it. So in this case, it was acetone, but it could be like the methane gas or like components in blood if you're looking at a biological application, different things like that.
Thank you.
Great. And Alex?
Yeah, for Catherine Stoll. For the
We're having a hard time hearing you, Alex.
is this better?
No.
Oh,
You might want to enter it in the, maybe type it in the chat.
Yeah. Try typing it in the chat.
all right. Okay.
Anybody else? And I know some of the folks here have to go to classes, so I know they will start leaving shortly, but anybody else here that has any questions for our presenters?
We have one from Wyatt.
Sounds
ahead.
good.
Wyatt? Well, yeah, go ahead. Oh, you might be on mute. We can't hear you.
No, I see you talking, but we can't hear you, unfortunately.
And I don't see Alex's question yet.
Hold on,
I
I'm
do
typing
want
it.
to enter yours in the chat as well. Perfect, thank you. So I think we have just a couple of questions getting in the chat. I thought I saw something from, oh, there's Wyatt.
Okay, so Wyatt, what additional sensor technologies can be approached with photonics in addition to chemical sensing?
Yeah, I guess there are a lot of different applications. Some people are using this for biological applications. So if you're trying to analyze blood samples, there were some during COVID, they were using it for COVID testing. So you could use it for applications like that. A little bit further down the spectrum, you can also use photonics for like LiDAR imaging, which is kind of another kind of sensing as well. Or you can do it for a mid-infrared imaging. So there are a lot of military applications, which is a similar process for those kind of mid-infrared detection applications as well.
Super, thank you. And then we have Alex's question. If the sensor that is connected to the FPGA, how would it be programmed with Verilog, or do you use another hardware programming application?
Yeah, that part I'm not as sure about. Most of the electronic engineering design was done by our collaborators, so I'm less sure about how the ASIC and the FPGA were programmed. I can ask them and get back to you for sure, but I'm not sure what hardware they used.
Super, great. Thank you. And it looks like we don't have any more questions, and we are over the hour. So I appreciate everybody's time, and I want to thank our speakers. Thank you so much. And that's the end of our program. So thank you.
We truly appreciate your time and coming to visit us.